The purpose of this lecture is to give an introduction to Chapter 3, cover most of the principles, and also to provide one example, but this will allow me to spend more class time on example problems while also providing you with another alternative to your textbook for learning the basic concepts. The major concepts that I want to get across in this lecture are, first, the concept of free body diagrams. What are they useful for? Why do we need them? And how to complete a free body diagram. And we're also going to be looking at the equations of equilibrium. I wanted to start off with a reminder, as I said in class last week, there is a problem set due on the 15th of October, and it covers those 8 problems, and there'll be the second opportunity for taking exam 1, which is scheduled for October 8th, next Thursday. So that's what the class time will be reserved for on Thursday, which is one of the other reasons why I'm having this recorded lecture, so that I can focus on Tuesday on example problems. The goals of this lecture are to look at the what, why, and how of a free body diagram, to introduce the equations of equilibrium, to consider the process involved in an analysis involving a spring or a pulley, and to consider the first examples of the application involving these concepts, and to get you ready to work these on your own in the problem set or the examples that we'll be going through in class. Some examples of applications for these topics that we can look at the start will be an example such as this crane, which is lifting a load, but to decide whether or not the straps can support the weight, you need to look at the forces in each of the straps and find out how those forces compare to the strength of the straps. To complete that analysis, you'll need to be able to draw a free body diagram and determine each one of the forces in the straps. Another example would involve this spool supported by a larger cable, and to complete an analysis to find out whether or not the spreader bar is designed correctly and the cables are strong enough, you'll need to complete a free body diagram of this geometry, and we'll learn how to do that in this chapter. Another example would be to look at this boat's towing pendant and decide whether or not the forces in the cables are going to exceed the strength of the cables, or are going to be within the range of strength range of the cables, and decide whether or not this is a stable setup. You might also use it for design of picking what size cable you'd need to have in order to keep this configuration stable. We're going to begin by looking at coplanar force systems. So basically we'll be reducing our applications to two-dimensional. And while the world is three-dimensional, you'd be surprised by how many times we have two-dimensional analyses still that are very useful in engineering practice. One example of a 2D or coplanar system is shown here. If the whole assembly is in equilibrium, then the particle A is also at equilibrium. So in fact, every part of this system is in equilibrium. To determine the tensions in the cables for a given weight cylinder, you need to learn how to draw a free body diagram and apply the equations of equilibrium. Free body diagrams are one of the most important things that you're going to learn in this course. And you're going to need it for other subjects in a year or 2 or 3 or 10 or 20. You'll often come back to the concept of when you're beginning a process, the first thing you'll want to do is draw a free body diagram. What is it? It's a drawing that shows all the external forces acting on the particular particle of interest. Why do you do it? It's the key to being able to write the equations of equilibrium, to be able to solve for the unknowns, which usually involve forces or angles in our problem. How would you do it? That is, how would you draw a free body diagram? First, you have to imagine the particle that you're trying to isolate and cut it free from its surroundings. you don't actually cut the cables. What you're trying to do is just isolate and imagine it on its own. Then show all the forces that act on the particle, and in our configuration, point A has one load pulling the particle to the left, one pulling it up and to the right, and one pulling it directly down, and that amount is the amount of the weight or the mass, which we know in this case we're given is 40 kilograms. When we think about the forces acting on a particle, we have active forces and we have reactive forces. Active forces tend to want to move the particle, and reactive forces tend to want to resist the motion, or incipient motion, that is, motion that might begin if the particle stops being at equilibrium. So we have to remember the difference between active forces and reactive forces. Next step is to identify each force and show all the magnitudes and directions. And we show the unknown magnitudes or directions as variables in our free body diagram. The example for our case that we've been considering, looking at the free body diagram at A, gives us an opportunity to recognize that we don't know the force on the cable from the left or the cable acting up and to the right, but we are able to determine what the force in the cable is associated with the 40 kilogram mass. And that's what we've done here, and our unknowns then are FD and FB. I wanted to give the hint that this is the time when you want to learn new habits of being neat and clear in your diagrams. This is what will serve you well in this class and beyond this class. In practice, in particular, you're going to need to make sure you have the ability to draw a free body diagram. Now that we have our free body diagram at A, it's time to apply the equations of equilibrium. The equations of equilibrium only assert that since this body is at rest, it's not moving or accelerating anywhere, the sum of the forces must be zero. If there were unbalanced forces, it would be on the move. So this particle is at rest, so the sum of the forces must be zero. That's it. That's our equation of equilibrium application. So we sum the various forces. In our case, force FB plus FC plus FD must be equal to zero, or the sum of the forces equal to zero. Because this is a two-dimensional problem, this can break down to simply having to look at the sum of the forces in the x direction and the sum of the forces in the y direction. In our case, both of these must be zero. This really doesn't depend on where we draw the axes x and y. They'll always be at 90 degrees, but we'll typically pick x horizontal to the right and y going up from the point of interest, but it could be in some other direction if you're going to find another direction for your axes more convenient. To write these in scalar form, we simply do have these two equations. The sum of the forces in the x direction equals zero, and the sum of the forces in the y direction are equal to zero. These are the two scalar equations of equilibrium for this planar analysis or coplanar system. They can be used to solve for up to two unknowns. We have two equations, so we can solve up to two unknowns in our problem. To begin to solve for the unknowns, FB and FD, in our case, we're going to need to now apply the equations of equilibrium. For this two-dimensional case, we're just going to remember that the sum of the forces acting on A must be zero, since it's not moving. As F is equal to ma, and it certainly isn't accelerating anywhere, there must be no unresolved force acting on A. So these three forces added together must be zero. That's conceptually what we're doing, but because this is a two-dimensional system, we're going to break it down into the x and y direction, and we'll sum the forces in the x direction, and set that equal to 0. Then we'll sum the forces in the y direction and set that equal to 0. We have these two equations, and we had two unknowns, and we're going to be able to resolve to find our unknowns in this case. So solving the second equation gives a value of FB equal to 785 newtons. Now, in this we can go back and use that in the first equation to get the value that FD is 680 newtons to the left. So we have our unknowns figured out after applying the two equations of equilibrium in our case. Let me introduce some concepts related to simple springs. A simple spring might look like this. We're going to have it be statically loaded. That is, we're going to be gradually applying this until we come to a F is the force being applied to the spring. It is in equilibrium, so it's not moving or bouncing anywhere. It's just stretching the spring to the particular extended amount. So if its initial length was L0, and by adding the F, the force, we had an additional displacement of S, creating a new length, L, we're going to be able to relate this stretch of the spring to the amount of force that would be required in order to create that stretch. For a simple spring, we can get the spring force being equal to the spring constant, and that's something that we'd need to know or measure for. And then we multiply that by the deformation of the spring to get the force that's actually acting on the spring. A way to write that with variables is that the force that's applied is equal to the spring constant times S, so K times S. That is, the spring constant times the deformation. So those are the symbols that we'll be using for simple springs. For cables and pulleys, we have to remember that cables can only tolerate tension. If you try to push on a rope, the rope won't sustain any push, any force that's compressive. It will only be able to sustain, a cable or rope will only be able to sustain a force in tension. When we have a frictionless pulley acting with that cable, we know that the pull on either side of that pulley must be equal. So T1 would be equal to T2 in this case. The cable can support only a tension or pulling force, and it must always act exactly in the direction of the geometry of the cable. Another issue that I should bring up is that when we think of smooth contact surfaces, for this class at this point we're talking about perfectly smooth contact surfaces. Something that you might know, something close to this, if you have an ice storm and you have icy sidewalks and you can't get any traction, then you have a fairly smooth surface, and that's the type of idealized surface that you should try and think of for this case. If an object rests on a smooth surface, then the surface will exert a force only on the object in the direction normal to the surface at the point of contact. So the idea being that you can't have any lateral load on a smooth surface, only a perfectly normal load. This is why, if you can keep yourself perfectly still on an icy sidewalk, while you can be relatively stable, but as you begin to try and exert a lateral force and begin to move on a slick, icy sidewalk, you won't be able to get traction, and then you have the problem of living on that surface. In addition to the normal force, the cylinder is also subjected to a weight W and T in this particular application. So we have a tension acting on the pulley, the weight of the pulley, and the normal force that's perpendicular to the surface of contact, because we have a perfectly smooth surface in which this pulley is in contact. Since the three forces are concurrent, all acting on the center of the cylinder, we can apply the equations of equilibrium to this particle, imagining just the center of the pulley, which is functionally the same as applying it to the cylinder itself. Is this true? No. Is this sufficient for our analysis of this system? Yes, in most cases. Now let's consider an example. In this example, we're going to have a 550-pound box suspended on a system of cables. The two cables are not oriented with exactly the same geometry. What we're asked to find is the forces in the ropes AB and AC that are needed in order to keep this box suspended and still in this geometry. Where do we begin? You should think about this. You want to start with a free body diagram. So we'll draw a free body diagram, then we'll apply the equations of equilibrium to solve for the forces in ropes A, B, and AC. When we apply the free body diagram at A, we have the force acting directly down, equal to the weight of the box, 550 pounds, that was given. And we have the two cable forces, one acting from A to B, that we're going to call FB, that's the force in that cable. And we also have a force FC that's acting along in the cable from the points A to C. Notice that FB on the left is inclined 30 degrees from the horizontal, but the geometry of FC on the right tells us that we should use the geometry of a 3, 4, 5 triangle, right triangle. Now that we have that free body diagram, we can apply our scalar equations of equilibrium at the point A, so that when we sum the forces in the x direction, we have a force coming in from the left, so it's pointing in the negative x-axis, so we say minus FB times cosine 30, plus, now notice it's positive because FC acts to the right in the same general direction as the x-coord axis, so we have FC times 4/5, which is the cosine of the angle on the right. So we set that equal to 0, and we have both of our unknowns in this first equation. Then we have our equation that comes from solving the forces in the y direction. So we sum the forces in the y direction to get FB times the sine of 30 plus FC times 3/5, that's the sine of the angle on the right, minus the downward directed force of 550 pounds. We have two equations with two unknowns. When we solve the equations in this case, we get FB is 478 pounds and FC is 518 pounds. Notice that the force on the right is slightly higher. Is this what we should have expected? Well, take a look at it. Its angle is slightly higher on the right than it is on the left. That's why it's carrying more of the weight. That inclination, being at a steeper angle, means that it's going to carry more of the downward directed force of 550 pounds. So it does make sense that the force on the right is slightly higher. I'll remind you again that we have 8 problems due on October 15th, the ones listed here, and the second opportunity to take exam 1 will be on Thursday, October 8th, with the same exam conditions that you had for the original attempt at exam 1. See you in class.